that we can start right now. We are on the line of about 1 hour and a half, so I don't know how much this will take, but I guess it will be ending up a bit late. For the foreign people, they are not used to have lunch or dinner at 9 or 10, so I don't know, maybe we can find something to. Anyway, if you don't understand something, you can say it, because my English can be a bit shitty sometimes. I am doing drinking, so I can feel that I speak better English, but it will be the same shit anyway. But if you don't understand, just say it, it's okay. Also, if you have any questions about what I'm saying, you can also ask. This is a training, it's not a presentation. So if you want me to elaborate more in any slide or ask anything, you just ask, just say. There's no problem with that. If there is a mistake, also say it, because I make mistakes sometimes. Okay. Sometimes, sorry. So, well, the slides are not very pretty, even that I use Windows, but that's the best I can do. So, I don't know which is your level in exploitation in here. Anybody in here works or makes his living about book hunting or exploiting? Yeah. Besides you and which we all know, you also a couple of ones. Then you are in the wrong room. I'm not going to say anything new. This is always the same shit. So there is not anything new. Yeah, you can leave. Do it. So, okay, do you hear me all? Because I don't want to use a mic, so I can type and. You all hear me? Yeah. Okay. Well, I will start. I don't used to make this kind of shitty slides because nobody uses to care, but because we are with Radar and we are a family. For those that don't know me, I will explain a bit. I have been working with computers for more than 14 years, so I'm quite old now. I started as system engineer working for Sun Microsystem when it was a thing back in the time, before Oracle fucked it up. I also worked as freelance developer, as pen tester in various companies, and finally I'm working as a Linux kernel researcher for Cosine. Also, there you have my names. I use a different name for every place. So, okay, the first thing that you must do if you didn't do already is update Radar. I guess you all are using Radar from Git. I hope so. And also, we will be using Node.js, which I love. And I don't know if you guys have Node 6.5, at least. If you don't, you should install it. And also having the Keystone plugin will be also useful to have. So, well, I will start with basic, really basic shit, because I don't know which is your level. So I will start with the most basic thing, like the memory map of a process. I don't know if you are used to it, but usually you have the, let me put the, okay, usually you have the binary in here, which has some read and execute area, another one only with read permission, and another one with read write but not executing. You used to have the heap, the stack, and all this shit is like libraries, BDSO, and bsyscall, which is from kernel, and things like that. But for now, it's okay with that. So this is the same for an x86 64 bits Intel, which the major difference is that you have bsyscall in here and bbar, but anyway, it's not really used. And this is the same, but instead of the memory map, is the sections of the ELF. Sorry for my spelling, but it's easy spelling. So usually all these sections that you see in here used to be used to be mapped in this area. So, well, we'll start. I will make a small kit, so we will see which is your level. And for example, if you have this code with this defined text, do you know where this text defined will be allocated in those sections? I guess many of you know. It's pretty basic.
Yes.
No.
You know where?
It's a defined, it's a constant.
Raw data.
Yeah. It's read-only data. So if you check with radar, you will see that it's in read-only data. And what about this global one, which is initializer? Wrong. It's data because it's initialized. BSS is when the data is not initialized, it's set to zeros. And now the one, no, not the one from BSS. And well, I'm cheating you guys. Where this is the story. Yeah, be careful because it looks like it's a stack variable, but it has a static in front of it. Anybody?
Data.
Okay.
I know data. Oh. Same as a global variable.
Yeah, if you put a static, it's global one. Will be saved. It really is not saved between executions. It's really in like a global. So this one is BSS, as you said, because it's not initialized and it has the keyword static. So even if you define it inside a function, it will be a variable, a global. So if you check it, it's BSS. Okay, now this one. This is the easiest one, I guess. The one, the serial ball in there, ball. This one, yeah, this one is a stack. Pretty obvious. And this is the last one, I guess. Yeah, heap. It will be in heap. That, well, if we check, this is the address. And if we look at the memory map, we will see that it's in the heap. So, well done. Well, basically, data is global data, which is initialized. BSS is global data, which is uninitialized, set to 0 by default. Read-only data is constants and defines. Stack for functional local variables, and heap for dynamic allocated data. And why I'm annoying you with this shit? Because it might depend where you are saving the data. The permissions will change. Which kind of data you can overwrite if you have an overflow will also change. And also different exploitation techniques might apply. So it's kind of important to know where you are, what you are doing, and what you can do when you are in different areas. So I will make an enumeration of common vulnerability types, which is pretty shitty because I guess most of you will also know, but I have to do it, sorry. It's like overflows, you have a stack and heap, are the ones that everybody knows. Null pointer difference, which they are not really useful in user space, but they also happen. Dynamic memory vulnerabilities, which are used after free, double freeze, or abuse of the dynamic allocator by overwriting the control structures and things like that. Also vulnerabilities which are related to handling numbers like sign issues or integers overflows, etc. Format strings, uninitialized memory, and race conditions. So, well, this is also, I guess this is the type that everybody knows, an overflow. When it happens, when you use, usually, because there are many ways how they happen. When you use insecure functions, on-write loops, when the copy size is improperly calculated or the programmer makes a mistake on on the size because of sickness issues, or even when you are using initialized variables. How can we exploit them? When you are in a stack, you usually, or you use it to overwrite the return address even in the stack. When you are on Heap, many people use it to abuse allocators, but it might depend on the allocator and the control structures and if they have patched it or not, and it's hell. I hate it. And also by overwriting function pointers which are nearby or next to the overflow, overwriting object pointers or vtables, which is much more like the function pointers, or using your brain and your imagination. Not every case is always the same. For dynamic allocator and vulnerabilities in dynamic memory, there are many different implementations of allocators for dynamic memory. You have ptmalloc, which is from glibc, pcmalloc, ngmalloc from nginx, the web server, the malloc for Firefox, and many others. For kernel space in Linux, we have these three, which are slab, sloop, and slop. And well, its implementation used to work differently, but they are basically the same. And well, when the type of books that you exploit are control structures override, they used to end up in a write what where type of book. Also, you could overwrite contiguous data instead of the allocator control structure. This is a piece of sheet of graphic that I tried to make, but these are control structures that used to hold the size, where is the next chunk, and things like that. The red ones are used chunks, and the green ones are free chunks. So if you make an overflow in here, you will overwrite the control structure and the next one, which is free, or if you keep doing that, will also overwrite this control structure and also the next chunk. There are also some other allocators which don't place control structures between chunks, but you will have another whole structure like this one here. So you will end up overwriting the start of the slab or the chunk. Anyway, I'm not going to explain here because each allocator is different head. Also, null pointer difference vulnerabilities. They used to be very popular for kernel space back in the day. Now they are not useful anymore because you cannot map memory at the address 0. So they are not useful anymore. I think that there is something right in here in the web. You can see. So, well, usually what happens when you exploit a null pointer, they are exploited for kernel space, as I said. So usually you map a memory page starting at 0, from user space. You put some data at that address, and you call to an IOCTL or a sysctl, which will cause a null difference in the kernel. Once you call that IOCTL or sysctl, you will be in kernel space, and the kernel space will start to execute the kernel, and a null pointer happens. Then when that null pointer happens, that will happen is that the kernel will be reading the address 0, which you mapped on user space. Because in x86, all the memory is plain. Okay, you have mapped the kernel memory and the user space memory, as I showed here. It's all together. You have a split here in 32 bits, which is 1 gig for kernel and 3 gigs for user space. User space cannot read kernel user page, but kernel space can read everything. So when you execute on kernel and a null pointer happens, it will go to read 0, and it will be reading data that you control, that you allocated in user space. So, well, if you are faking a structure or whatever the kernel is looking in that 0 address, you can fake it and try to gain access. Whatever. This will be an example, for example. you map the 0 page, and well, here there is a structure. We have some random data, 25 bytes. Have a function pointer in here. So okay, we copy to the 0 address that we allocated. We copy in here this structure that we made. This structure, the function pointer points to function pound, which is in here. And we call to the IOCTL. When the IOCTL gets executed in kernel area, okay, this is red, so you cannot see the pointer. When it gets executed in kernel area, here in the left, well, we have a structure called demo, which has a pointer to a structure which got null. Don't know why, but it got null. And then if you try to access demo and that null pointer and call the function pointer, you will be calling what the user has in user space. Well, and this one-liner basically changes your process to root. But it's basically that. Anyway, null pointers are not useful anymore. There is a protection and very good placed. So they are not really useful. Then we also have use after freeze, which are kind of trendy right now for browsers, kernel and everything. Use after freeze is the new thing, probably. So well, okay, you allocate 16 bits in here. You free those 16 bits. You free that memory, and then you allocate again 16 bits. If you still use the first pointer, which was freed, you will find the second allocation. Sorry, because my explanation is a bit shitty sometimes, but let me clear that. Okay, so basically you make an allocation in here, you free that allocation, and you allocate here once again. So if you use the first pointer, it will be pointing to the second one. Basically, both pointers will point to the same. You can see it in here. This is the execution of this program. You see that it prints pointer 1 and pointer 2. Then it makes the new allocation, and pointer 1 and pointer 2. And you will see that at the end, both pointers point to the same memory area. So, well. Then we have vulnerabilities like for number, when you are handling numbers. This is one type. Can you see the vulnerability in here? I guess it's pretty obvious also. Yeah.
By the time malloc locate that in the
It might depend on the allocator. Dynamic memory is usually hell. Its implementation is totally different. Some implementations make like pools based on size. So if you allocate chunks of 52 bytes, then all will go in the same areas. It might depend on the allocator. No, it might depend totally on the allocator. For glibc, if you are in user space with one thread and you allocate an free and you do another allocation of the same size, it will end up in the same place. But with one thread, the allocations of the same size, etc. But it might depend on the allocator totally. It's a fucking hell. I mean, it might depend if you are working on a browser, if you are working on a kernel, if you are working in user space with glibc, even the versions, it's not for granted, but usually that's what happens on glibc. So, well, we have for number handling, I guess the vulnerability is quite easy. Please tell me, someone.
Negative input.
Okay. Yeah, it's for when you here we are converting a string to integer to a signet one. And here we make a check that that integer is not bigger than 80. Okay, but that's, it's a signed integer, so we can input a -1, and it will do okay on this check. And when it arrives here to the mem copy, the argument is always unsigned. So it will convert that signed one to unsigned, and it will overflow for code. So here you have an example. If you put many, say copy 4, and you put a buffer, it will copy 4 A's. If you say copy 90, it will not do anything because 90 is over the check. And well, we check this number in X, and we get the negative and the unsigned int and unsigned one. So if we input that number, and again the same buffer, will cause a huge buffer overflow. Just by itself, it's not a vulnerability and integer handling. The problem used to come when the programmer is using that bad integer to do a copy or whatever. So you will need to find if the programmer is using that number again, then there might be a problem. Also, uninitialized values are also funny, or they still happen sometimes. So what's the problem? This is kind of fishy example, okay, because kind of different. It's kind of easy to explain. So let's suppose that we have here a variable in the stack, and we have here a check if we want to set the variable to a value or we don't want to do that. So what happens in here is that if you don't put a value in a variable in the stack or even in the heap, if the heap have been used and you use it again, you will get the heap with data, which is basically dirt. It's not your data; it's data which was allocated previously. So if you use that variable without initialization, the data that you will get, it will be kind of random or previous shit that was in there. So there are ways to exploit this. For example, if it's a variable in the stack, you will need to find execution paths that fill the stack up to the desired area that you want, fill it with data that you need, and then call the execution path which is using the unity. You know what I'm trying to say. And it will end up using a value that you put in there before. This can happen in heap and stack usually. So format strings, they were also pretty famous back in the day. Not anymore, but well, they are still exploitable. So you can see in here that we read some data in buffer, some input from from the standard input, and then we print it directly. In the first argument of print functions will be a format string, so our input will be the format string. So if we call that program, it will ask us for input. We input XXX, and it will give us the data which it will be popping from the stack. It's useful for information leaks, and you can also perform write what were attacks with it. So as a bonus, well, also info leaks are also quite necessary nowadays. It's time they are even more important than before, because with modern mitigations, you need some information about the memory mapping to make a successful attack. So many times right now you need info leaks. Some ways to look for info leaks or kind of books that produce info leaks are reading not null terminated strings, because there was a bad size calculation when calling to some function and the string wasn't properly terminated. So it will keep reading. When you read that string, it will keep reading till it finds a null byte, and it will leak some data. Format strings are also useful for info leaks. Reading initialized data, it's also useful as a leak. Or controlling the size of a read-write operation, like I don't remember the name of the book from OpenSSL, the last one, which was leaking data in SSL, Heap. That was a memory leak because of the size in a read-write, which I think, if I remember, it was you can control the size of the read past the buffer of the packet. So okay, there are my fonts are missing. Nowadays, there are many mitigations against many of these attacks. Some of them are implemented on kernel or hardware level, as address space layout randomization. This one is implemented by the kernel. Or also you have permissions on the memory maps, on the memory page, like read-write, or the last which was added was the no execute bit for a memory page. There are also protections which are implemented on compiler or during compilation time, like Fortify, Stack Protector, make your binary position independent, checks for the heap consistency, or making the relocation table read-only. There are also other ones which can be enabled and disabled during runtime, such as malloc check, which is implemented by the glibc and is used basically to also check the consistency of the heap. For the address space layout randomization, I guess that all of you may know it. It's one of the most famous ones. Well, in order to perform a successful attack, you need to know some information about as I said before, about the memory or the memory map of the process that you are trying to exploit. So this mitigation tries to randomize as much as it can from the address space of the process, so it will try to difficult your exploitation. It won't stop any attack. I mean, it won't stop an overflow, a format string, or whatever. It will only make you harder to exploit it. But it doesn't stop the attack itself. It just fucks you, but it doesn't stop you. It stops the attack. So basically, what you usually have is when you build a linear address or your address space of your process, you used to have on 32 bits, you have 12 bits for the physical address and 20 bits which are virtual or for the address space. And when you add the address space layout randomization, what happens is that it adds only 8 bits for the virtual address and 12 for the physical ones, and the rest are random. Okay, so for 32 bits you will have 12 bits of entropy. Here you can see an example how these three nibbles, well, the binary, if you don't build it with position independent execution flag, it will be always in the same area. But the libraries, the stack, and the rest, it will be random by 12 bits. These three last nibbles are always the same. The 12 bits are also always the same, and the 8 bits, sorry, the first byte is always the same, and these three nibbles are the ones which are changing all the time. So, well, you can enable and disable it by writing in proc file system or by using a sysctl. Unlike in Windows, here there is the trick that I don't do Windows, but I know that there are some tricks, or they used to be some tricks, like some libraries weren't compiled to be relocatable, so you will always find the same DLLs at the same address space always. So making a rob gadget was really, really easy if one of those libraries was loaded. Here in Linux, that never happened like that. There were only two cases, which was Linux Gate, which was mapped always in the same address space, but it was like many years ago. And bsyscall, which is a kernel part which gets mapped in the user space of the user space area, so you can see it in the memory map from the process. Also, as I said before, the randomization doesn't apply to the binary unless you build it as a position independent executable. Only applies to stack, libraries, heap, etc. In some scenarios, the randomization is not applied or it doesn't work as intended. So we can take advantage of that kind of situations. For example, when forking, when you fork, you always inherit the same address space and the same layout than from the parent. It will be basically a copy, a one-to-one copy of the parent process. So if the parent process has one memory map, you fork and the child will have the same. You fork again and the child of the child, and it will have the same memory map. Also, for all the kernels in 32 bits, there was some kind of it wasn't bug because it was intended. But if you remove the limit for the stack size limit, the address space on 32 bits is so small that you only have 3 gigabytes for your address space in user space, and if you remove the limit for a stack, the stack can grow infinitely. So to avoid that, it always places the stack at last and to let it grow, and the process and the user or the rest of the process, the executable in other area. So you will end up having everything statically or having the same address always. I think that this doesn't work anymore.
Question: I assume the address space gets
If you fork, it will have the same address space as the. If you fork again, the same. It's always a same address space.
Exact. When you,
What do you mean? I didn't get you. Oh, the XB. No, that will generate a new one.
Okay.
I'm just talking about fork system. Just fork. XB will make a new one. Okay, so here you have the fork same. I think it's the forked one, or what is it? Yeah. Well, padre is father or parent in English, in Spanish, and hijo is child. So here we can see that we print the stack, the heap, and some code, which is this function, the address of that function, and we print that from the parent, and we print it from the child. As you can see, the stack is the same, the heap is the same, and the code is the same. So well, it only applies to fork, not for XB. And well, this was I was talking before about, which was limiting the stack size, which as I told you, it is not a bug or whatever. It was intended. This is in fact from an old kernel, and you have that if the stack limit is infinity, then it will disable the address randomization. I think that doesn't work in newer kernels, but I haven't tried. For the old ones, it definitely works. Only for 32 bits. And here you can see an example. I think that this one is the normal state. So it will randomize. Here you can see 7760. Okay, that's LD, and here it's different. Okay, for the same library, here is in 60 and here is in E3. And if we set the limit of the stack to unlimited, you end up having, for example, libc, the executable code of libc, and we will have it on 29, and here also in 29. You cannot probably see it because it's really small, the font, but that was also a trick when you were exploiting or making a exploitation of a local binary or a set UI binary or things like that. But really, if you are exploiting a local binary, you can brute force. You can use brute force probably much better than this. So okay, for address space randomization, how can you deal with this? When it's possible, or you have the possibility, you can try to brute force, to apply brute force. If the stack is executable and you have your payload or your shellcode in the stack, then you can use a jump to the stack or a call to a register which points to your controlled data. You can also use ROP, return-oriented programming. If the binary is not position-independent executable, you can use the old red2 library techniques, or you can use information leaks to take hints about how the layout of the address space.
Nowadays, the stack is
No. That was back in 2002 or something like. No. I said if the stack is executable, which is not really common. You will only find that on CTFs or maybe a strange Unix flavor for a strange architecture or something like that. But it's not anything. It's no longer a thing. Okay, for the no execution bit, it's implemented by hardware or also by the kernel. It can be done on kernel space also without hardware support, but lately all the modern Intel processors have hardware support to mark up memory page as only executable or only read and execute, things like that. It marks the pages without code, like heap, stack, as no executable, and the page with code they mark they are marked as read and execute without write permission. Okay. As I said before, the pages with data where you need to write will be read-write but not execute. And ideally, the combination of read and execute never should exist, but you can make it. Happen. I mean, it's not impossible to do it.
read, write.
Yeah, write and execute. So, well, so basically what this does is preventing that you write something into the user space and execute it. So if the code was not shipped with the binary and the libraries, it won't execute, usually. That's the point. So you can enable and disable this for the stack using a binary, which is called xstack. If you call this binary in your system and apply it to a binary, it will enable and disable the execution of the stack of that process. It's not a thing anymore, but some kind of programs still need to execute code in a stack. So sometimes somebody may need it. Also, the hardware support, you can check it on your processor. You can see here that it's NX. And well, you can just edit the binary sections and just mark the headers of the section as read-write or whatever. Here you can see a memory map where you have a section of the binary which will be executable and readable, which this is code of the code of the binary. Here we have read, write, and execute because this doesn't have the BitNX protection enabled. So you can find a combination here of read, write, and execute in Heap, read, write, and execute in a stack, etc. But this one, which has the protection enable or whatever you want to call it, it never has the combination of write and execute. TM, TM, debug memory or memory maps, debug memory map. So, well, here we have an example of trying to jump to a stack with code, which is basically an obsolete. And when the protection is enabled, you will have a segmentation foul, because even if it's a code, that page doesn't have permission to be executed, anything on that page. So you can deal with this. Well, you can use the old return to library techniques, or you can use ROP or ropchains. Well, the old return to library attack used to be, if you have a stack frame in here, you used to have always your local variables, your base pointer, and the saved return address. And when you perform an overflow, you will overwrite the return address and point it to another part of the binary. For example, a part of the binary where it calls to system or to the relocation of the system call, and then set up the stack with the arguments you can you want to use for system. This way, instead of executing a shellcode, you are executing the code which is already present on the binary. You can also use ROP, which is, well, this is quite messy graph, but basically, if these are the return address, if this is a stack, you have multiple return address in here, and you will execute, point to one part of the binary, execute a couple of instructions, then a return. It will pop another address of the stack. It will execute some instructions. It will return and pop another variable in the stack, etc., etc. Another modern protection is stack cookies, or stack protector, I guess it's called in Windows or something like that, which what it does is placing a cookie, or also called canary, they also call it canary, in between your local variables and your base pointer and return address. So if you want to overwrite the base pointer or the return address, you will have to overwrite the cookie. And always before calling to read, there is a check here. We'll check the cookie, and if the cookie has been overwritten or the value is not the one which should be, it goes this branch and the execution finishes. The cookie is okay, it goes this other way and everything goes well. The stack cookie used to be saved in the what is called thread local storage, and is static for the whole execution of the program. If you fork, it will have the same stack cookie also. So anyway, if you check that thread local storage and the address where that cookie is allocated, you will find out that it ends up being allocated at I think it was data or something like.
Yes.
What does it stand? Yes, it's a segment. It was used in 32 bits. Joder, este segmento, ¿cómo coño? Yo lo uso siempre en 64. CS, GS, segment register from 32 bits. It's not anymore used usually in 64 bits. But well, actually the TLS end up in I think it's some kind of like data, which is a read write page, but not really important. Some things to keep in mind. Usually it's only enabled when the buffer or the local variables of the function are bigger than 8 bytes. The original cookie is stored in TLS, which is read-write. If you can find it, you can overwrite the original one. The cookie is always placed before the base pointer and the return address. It doesn't prevent overwriting local variables, so you can still overwrite or make an overflow and overwrite any local variable. And well, the cookie doesn't change during the program execution. So if you fork, it's consistent with forks and will also be the same. How you can deal with it? Well, you can try to make a brute force, use brute force when it's possible, like on services based on fork. You can use information leaks for leaking the cookie. Or if the overflow happens in any other area which is not the stack, then you don't have any problem with the stack cookie, because it won't. It's not, if you are not having an overflow in the stack, you don't care about it basically. Then you have the position independent executable. What it makes is generating your code to use always relative address. Okay, instead of using absolute address for anything, it will always use relative ones. You can enable it when building using these flags, and in 32 bits is a bit messy, the code which it generates. You can see it much more easier in here. That when you are referencing, for example, this is a static variable, it will do it relative to the instruction pointer. It will take the instruction pointer, it will add or subtract some value, and get the address of the variable or whatever you are referencing. So it will always use relative addresses instead of absolute one. That way, the address layout randomization protection can position your code anywhere in the address space. So here you can see, you can see a binary which doesn't have the position independent. It wasn't compiled with position independent, so the address will be the same for the binary. 76 or no, or this is with it enabled. Sorry, the protection is enabled, so the addresses change between execution for the binary. How can you deal with this? Well, unfortunately, this is one of the worst things to deal with, because you will need a memory, an information leak to be able to make an idea of the address space. And the only other option will be a brute force, which is not really useful in here. Okay, so for heap consistency checking, we have some runtime checks which are implemented by glibc, and it can be enabled and disabled during runtime. And you can set this environment variable to 0, to 1, or to 2. It will ignore any corruption. It will just warn you about the corruption, or it will stop the execution of the program if it finds a corruption. Well, this is a pretty common heap overflow. We have one 10 bytes allocation, another allocation of 10 bytes. Both allocations are supposed to be contiguous, 10 bytes in here. You will have some control structure here in between, and you will get another 10 bytes in here. So, well, and here we have another allocation of 10, and then we free these two. So when you make the free, it's when the glibc detects that it has been an overflow. I mean, if you don't make a free in here, if you don't free this memory, there is no way that glibc knows that there has been an overflow. So well, as long as there is not a free, your program or the program will continue the execution, and you can overwrite or overflow any contiguous memory area. The only problem will be if there is a free or any other glibc dynamic memory function which will check for the consistency. Okay. There are a couple more of protections, so I guess we can have a break if you